In this video tutorial, we'll take a look at the concept of mathematical induction, and we're going to start with a story. There's a legend about a famous mathematician. His name was Karl Fredrick Gauss, that when he was in elementary school, his teacher at the time wanted to give the students something to keep them busy because he had some work to do. So he asked the students to add up the first 100 numbers from 1 to 100. So this is the sum they were asked to find. And it wasn't very long at all before Karl Fredrick Gauss came up and told the teacher what the sum was. And the teacher was amazed and asked Karl how he did this. So what he said was, he said, I took the fourth number and the fourth last number and added them together and got 101. 4 and 97 add to 101. As do the third number and third last number, 98 and 3, also add to 101. As do 2 and 99, and also 1 and 100. So you've actually got 50 pairs of numbers that add to 101. And supposedly Karl Fredrick Gauss said to his teacher, and I know something you haven't taught us yet called multiplication. And so if we multiply 50 by 101, we get 5050 for the sum of the numbers. So that's just an example of, this is actually a series, a sequence of numbers added together, and there's actually a formula for finding the sum of that series, the sum of the first n positive integers, basically. And so we're going to take a look at conjecturing that formula and proving it true. Now, the first sum is, of course, just the number 1. The second sum would be the sum of the numbers 1 and 2, which, of course, is 3. S3 would be 6. 1, 2, and 3 add to 6. And S4 is 10, because if you take that 6 and then add a number 4, you get 10. Now, here's a pattern, and we can use this to find a formula for the sum of those series. This 1 is actually 1 times 1 plus 1 over 2. That does work out to give you 1. 3 is actually 2 times 2 plus 1 over 2. 6 is actually 3 times 3 plus 1 over 2. Notice these numbers here, the 1, 2, 3 here and the 1, 2, 3 here, are actually the number of the sum. The first sum, the second sum, the third sum. So for the 10 here, it's actually, 10 is actually 4 times 4 plus 1 over 2. Which is actually 4 times 5 over 2, 3 times 4 over 2, 2 times 3 over 2, etc. So the 5050 it's the 100th sum, so it's 100 times 100 plus 1, or 101, over 2, and that works out to 5050. Now, we're going to prove this works for any, like 1 to however far you want to count to find the sum. And one of the important things in proving mathematical formulas true by mathematical induction is that any particular sum is the previous sum plus the next term. So for example, this 10 here is the sum of the first 3 numbers. See, 1, 2, and 3 would be the sum of the first 3 plus the next term. The 4 here would be, in this case, the next term, the 4th term. So for example, 10 is 6 because that was the third sum plus the next term. And we can generalize that if you want any sum, let's say the k plus first sum, it's the sum before that. So that would be the sum of the first k terms, where k, of course, is exactly 1 less than k plus 1, plus the next term. The next term after this sum would be the k plus first term. And that idea is fundamental in using mathematical induction, or proving by mathematical induction. So flipping over to the next page, it looks like the sum of that series is whatever n is. So we'll find the sum of the first 20 terms would be 20 times 20 plus 1 over 2. So the sum of the first n terms is n times n plus 1 over 2. Or we could write it this way: 1 plus 2 plus 3 up to n is equal to n times n plus 1 over 2. So our goal here is to prove that that is true no matter what n is, no matter how high n goes. Now notice that the nth term is n. So the 93rd term is 93, the 2074th term is 2074, etc. So that's the nth term. Now, I'll generalize this shortly here, but the way mathematical induction works is you show that the formula works for the very first case. So, and of course, I'm saying that this is true for n equals 1 up to whatever. And of course whole numbers only. So the S1, or the sum of the first terms, of course, is just 1. And in the formula, if I put 1 in place of n here, it's 1 times 1 plus 1 over 2. So there's the 1 times 1 plus 1 over 2. There's the 1 substitute in place of n in both of those cases. And of course, that does work because this is 2. And 2 times 1 is 2, divided by 2 gives you 1. So that does work out to 1. The formula does work for the first case. Now what you do next is you assume that the formula works for some number k. So I'm saying now, I'm assuming that the sum of the first k terms is, I'm putting k in the formula here or over here, it doesn't matter which, is equal to k times k plus 1 over 2. And our goal is to show is no matter what k is, that it's going to work for the next value of k, which would be k plus 1. So we're going to show this pattern holds for the next integer after k, which would be k plus 1. So if I put in the formula here k plus 1, the sum of the first k plus 1 terms, then this would be k plus 1. And we put k plus 1 here, so we have k plus 1 plus another 1 in the brackets. And of course that simplifies to k plus 2. So our goal now is to say, well, we're assuming that this is true, and show it's true for the next integer k. So that's what we're going to show on the next page. Now, remember, the nth term is n. We'll need that in the next page. So this is our assumption, and this is what we have to show, that holds given that if this is true. So remember, and again, the sum of any sum, this is the k plus first sum, is the previous sum plus the next term. So S sub k, this is S sub k here, this is our assumption, k times k plus 1 over 2. And remember the nth term is n, so the k plus first term is k plus 1. So we need to show that this is going to work out to k plus 1 times k plus 2 over 2. Now, I need to get a common denominator. There's a denominator of 1 here, so I've multiplied this top and bottom by 2, so I have a common denominator now. And I would just expand this out. I expand the k in here. K times k is k squared. K times 1 is k. Multiplying the 2 in here, this would be 2k and then 2. And if we add the k and 2k together, we get 3k. Now, if you factor this, what adds to 3 multiplies to 2 are 1 and 2, so this would or we could expand this out. This would factor into this, or if we expand this out, k times k is k squared. This would be 2k, this product, and another k is 3k, and 1 times 2, of course, is 2. So the fact that these are the same means that the formula works for the k plus first term, or k plus first sum, sorry. So because it works for the k plus 1 term, as long as the assumption is correct, that means that this formula is true. The sum of the numbers from 1 to n is n times n plus 1 over 2. Where, of course, n can be any natural number. Now, this method of proof is called mathematical induction. And there's 2 basic steps here. The first step is to show that the formula works or the result's true for the very first case. Usually when n equals 1, but there are some times when the formula might start at a number different than 1, you know, maybe 2 or 3 or 5 or something like that. The next, after you verify it's true for the first case, the next step is to show that as long as the result is true when n equals some arbitrary number k, that it's true for the k plus first term. And that's actually the crux of mathematical induction. If it's true for some arbitrary integer k, and it's always true for the next number after it, then that covers all cases. Because as long as you show it's true for the first case, then, well, if k happened to be 2, then it's automatically guaranteed to work for the number 3. If k happened to be 3, if it's true for the next case, it automatically works for 4. And that's how it guarantees that it works for every number above 1, or whatever the first case happened to be. Now, before we get into some examples, the theory of falling dominoes says that as long as you place the dominoes properly, and as long as, in order to get them to all fall down, if you knock over the first one, okay, then you start, it's kind of like you start the ball rolling. And if somewhere in the middle you choose an arbitrary domino and say, well, that domino is going to knock over the one after it, and no matter which one you pick in the middle, if you pick this domino here, it's going to knock over the one after it, then that guarantees that all the dominoes are going to fall down. So you have to start by you knocking over the first one, but then you don't have to touch any other ones, because if you take a look at every single domino in the middle here, it's always going to knock over the next one, and that's what guarantees that they're all going to get knocked down. So let's take a look at a few examples, and if you're not too sure about this middle part where you say assume it's true for some arbitrary integer k and then show it's true for the next integer, well, at the end here I'm going to show you what happens when you try to prove something true by mathematical induction that isn't true. Okay, so we'll get into that assumption if you're not comfortable with this assumption thing. So example 1 is to prove that 6 plus 12 plus 18 up to 6n, so that's the general term, is equal to 3n times n plus 1. So this is a formula for calculating the sum of actually all the multiples of 6. That's what it is. And so it says for all n contained in natural numbers, which means for n equals 1, 2, 3, 4, 5, etc. So step 1, verify the result is true for the first case. So if n equals 1, if we put 1 in place of n here, we should get the first term, the first sum. Okay, so S1 is 6. So if we put 1 in place of n here, it would be 3 times 1, and then in the brackets we'd have 1 plus 1. Well, that's 3, and that's 2. 3 times 2 works out to be 6. So the fact that those are the same means that it has been shown true for the very first case. So the result's true for the first case. Step 2, assume the result's true for some arbitrary integer k, and then show that no matter what k is, that is true for the next value of k, which would be k plus 1. So, and if you forget, look back here, 3n n plus 1 is the formula, 6n is the general term. So 3n n plus 1 is that form we're trying to prove true. So if we put k in place of n, the 3n times n plus 1 would be, the sum of the first k terms would be 3k times k plus 1. So that's that formula at the end of the previous page, the end of the series. So we're going to assume that that's true and show that if no matter what k is, that the sum of the first k plus 1 terms would be equal to, and in place of n, where n was, we would put k plus 1. And so this would be k plus 1 here, plus this one. And of course, that just simplifies to k plus 2. So that we're assuming that this is true and showing that no matter what number k is, that it's going to be true for the next case, that the sum of the first k plus 1 terms is 3k plus 1 k times k plus 2. And I think it was on the very first page I referred to this sum property. The sum of k plus 1 terms is the previous sum plus the next term. So we use that to show that as long as this is true, that this is going to be true. So the sum of the first k terms is this 3k k plus 1. So in place of this, we'll put the 3k k plus 1. Remember the nth term was 6n in that series, so the k plus 1 term would be 6 times k plus 1. It's just 6 times the term number. And our goal is to show that that is the same as this. Now if we expand this out, 3 times k is 3k squared, 3 times 1 is 3k, and then expand the 6k and the 6 in here, we get 6k plus 6. And then 3k and 6k add to 9k. So this, again, we're trying to show it's equal to this. So notice you can factor a 3 out, and then we're trying to factor k squared plus 3k plus 2. Well, what adds the 3 multiplies the 2 are 1 and 2. So this will factor into k plus 1 times k plus 2. So the fact that they're the same means that no matter what k is, it's always going to be true for the next number after k. So that's what guarantees that this formula is going to work for every single case. So that means that 6 plus 12 plus 18 up to 6n, whatever n is, would equal 3n times n plus 1. So if we want to, for example, find the sum of the first 1,000 multiples of 6, then n would be 1,000. We would go 3 times 1,000 times 1,000 plus 1, and that would give us the sum of all those numbers. Here's another example. We're asked to prove that 2 plus 8 plus 14 plus, and this is the general term, 6n. These are almost multiples of 6, except they're actually the 4 less than the multiples of 6. We take the number n and multiply it by 6, but then subtract 4. So we get 2, 8, 14, etc. We're asked to show that the sum of that series is n times 3n minus 1. So if we want to find the sum of the first 50 numbers here, it would be 50 times 3 times 50 minus 1. So the first step is to verify it's true for n equals 1. So if we put 1 in place of n here and here, we should get 2. So S1 is 2, it's the very first term. So if we put 1 in here, it would be 1 times 3 times 1 minus 1. And so that's 3 minus 1 is 2, so we have 1 times 2, which of course works out to be 2. So it is true for the very first case. So step 2 is to assume it's true for some arbitrary integer k and show that no matter what k is, it's true for the next integer after k. And if you forget, this is the general term. Term n was 6n minus 4, and this is what the sum is, n times 3n minus 1. So the sum of the first k terms would be k times 3k minus 1, that formula from the previous page. And we're going to show that as long as this is true, that the next sum is going to be true. So if we replace k with k plus 1 or n with k plus 1, then this would be k plus 1, and we're putting k plus 1 here. So we need to expand this out. So this would be 3k plus 3 minus 1. Now the plus 3 minus 1 works out to be 2. So basically the sum of the first k plus 1 terms should be k plus 1 times 3k plus 2. So back to this sum formula, the sum of the first k plus 1 terms is the previous sum plus the next term. Well, the sum of the first k terms is, from our assumption, k times 3k minus 1. So we substitute in place that k times 3k minus 1. Remember from the previous page, the nth term was 6n minus 4. So the k plus first term, we would substitute k plus 1 in place of n. And so it would actually look like this. We would go 6 times the k plus 1, because we're looking at the k plus first term, minus 4. And that does simplify to 6k plus 2, because this would be 6k plus 6, so there's the 6k. The plus 6 minus 4 works out to plus 2. So that's where the 6k plus 2 comes from. That's the k plus first term. Now if we expand this out, k into here, we get 3k squared minus k plus these two terms. And of course negative k and 6k add to 5k, so that's what we have. And if you factor that, you do get k plus 1 times 3k plus 2. We could just check this. K times 3k is 3k squared. This would be 3k, and this product would be 5k, or 2k more to make 5k. And then 1 times 2, of course, is 2. So the fact that they're the same, that this sum of the first k plus 1 terms does work out to what the formula says it's supposed to equal, that guarantees that the formula works. So 2 plus 4, 2 plus 8 plus 14, etc., up to 6n minus 4 is equal to always n times 3n minus 1 for all n. Okay, so last example before we get to the fallacy one, we're asked to conjecture a sum formula for this. So this is the first four terms of a series added together. So the first sum is 1 over 1 times 2. So of course that simplifies to a half. 1 times 2 is 2. The second sum would be the first term, which is the half or first sum, plus the next term, which would be 1 over 2 times 3. And so we have a half plus 1/6. And if you get a common denominator, 1/2 of course is 3/6. 3/6 and 1/6 add to 4/6, which reduces to 2/3. So that's the second sum. The second sum means the sum of the first two terms. The third sum would be the sum of the first two terms, which is the 2/3, plus the next term, which would be 1 over 12. And if we get a common denominator, multiplying the 2/3 by 4 top and bottom, we get 8/12. 8/12 and 1/12 is 9/12, which reduces to 3/4. And hopefully you're seeing a pattern here in the 1/2, 2/3, 3/4. The fourth sum, for example, would be the third sum. The 3/4 is the sum of this term, and this term, which is the 3/4, plus the next term, which would be 1/20. If we get a common denominator and add them together, we get 16/20, which is 4/5. And so if we take a look at the sums, and I'll write them all out here, the sums are 1/2, 2/3, 3/4, 4/5. Notice that the top number is the term number, and the bottom number is just one bigger. So we could conjecture, it seems like the sum of the first n terms is n. So this is the term number. The fourth sum has a 4 on top. The second sum has a 2 on top. And the denominators are all one bigger than the numerator. So it looks like the sum of the first n terms is n over n plus 1. It looks like that. That's not a proof, but that's a conjecture. It looks like that's true. We're going to prove that that is true. So we're asked to prove that that series sum is n over n plus 1. And then we need, in the middle of our proof here, to find the general term for this. And so notice that the general term is, it always has a 1 in the numerator. And what's multiplied in the bottom, in the denominator, is, notice the first number is actually the term number. That's the third term, so it has a 3 at the beginning, and the number after it's 1 bigger. That's the fourth term right there, has a 4 here, and this is 1 bigger. So the denominators are n times n plus 1. The term number times 1 bigger than the term number. So we're asked to verify it's true for 1. So of course the sum of the S1 would just be the first term, would be a 1/2. So if we put 1 in place of n here, we would have 1 over 1 plus 1, which of course is equal to a 1/2. So the formula does work for the very first term. So step 2, we would assume is true for k. So assume that S sub k, the sum of the first k terms, is k over k plus 1. And then prove that, or show that no matter what k is, that the sum of the first k plus 1 terms is, and if we put k plus 1 here, we get k plus 1 in the numerator and k plus 1 in the bottom. So it would simplify to k plus 1 over k plus 2. We're asked to show that that's true as long as this is true. So those are those two formulas from the previous page. And again, any sum is the previous sum plus the next term. So the sum of the first k terms from our induction hypothesis or assumption is k over k plus 1. And the kth term, remember, it was 1 over n plus 1, so it would be 1 over k plus 1 times k plus 2. Now, if I'm going to add these, I want a common denominator. So I need to multiply. Notice they have a k plus 1 in common here, but this one doesn't have the k plus 2 that this one has. So I'd want to multiply that top and bottom by k plus 2. Now I have a common denominator. Expanding the k in here, k times k is k squared, k times 2 is 2k, and of course plus this 1 here. Now, k squared plus 2k plus 1 factors into k plus 1 squared. What adds to 2 multiplied as 1 are 1 and 1, so that's why it's k plus 1 and another k plus 1, or k plus 1 squared. So this k plus 1 in the denominator would divide out with one of these, and so we're left with k plus 1 over k plus 2, which is what we wanted to show. Okay, so that S sub k plus 1 formula is equal to this, so the formula works. So it's true for k plus 1, so 1 over 1 times 2 plus etc. is equal to that sum formula is equal to n over n plus 1. That was the last example of proving by mathematical induction, so I'll call this one an induction fallacy. I've actually created a series, and there's nothing wrong with the series, and I'm saying, well, I think that this, or I want to show whether it's true, that the sum of all these terms is n squared plus 3n minus 3. And I've actually made this so it actually does work for the first case, but it doesn't always work. Okay, and I'll show how that works here. So by mathematical induction, I want to show that if I put 1 in place of n, that it gives me the very first sum, and S1 is 1. So if I put 1 in place of n, 1 squared plus, and 1 here, 3 times 1, minus 3. So that's 1. This would be 3, and then minus 3 in the end, and that does work out to 1. So it seems like it's true. It does work for the very first case. This does work if n is 1. So we would want to, so it is true for 1. So the next thing we want to do is to assume that this series does have a sum of, if for the first k terms, the sum of the first k terms would be k squared plus 3k minus 3. So that's our assumption, our induction hypothesis is called. And to prove that no matter what k is, that the sum of the first k plus 1 terms would be, and of course we would put k plus 1 in here, so it would be k plus 1 squared plus 3 times k plus 1 minus 3. And if we expand this out, k plus 1 squared is k squared plus 2k plus 1, expanding the 3 in here, and then we had this minus 3 in the end. So let's just collect the other like terms. 2k and 3k add to 5k, and of course these subtract to 0, so we just have the 1 in the end. So that's what the sum of the first k plus 1 terms is. Now, remember, any sum is the previous sum plus the next term. So s sub k plus 1 is s sub k plus the next term. Well, s sub k is this, the k squared plus 3k minus 3. This is the general term, is 5n minus 4. So if we want to know what the k plus 1 term is, we put k plus 1 in here. And again, we're trying to show that this works out to k squared plus 5k plus 1. Well, 5 multiplied in here is 5k plus 5. And if we collect together the like terms, we get, there's only one k squared term. 3k and 5k is 8k. Negative 3 plus 5 minus 4 is minus 2. But notice that this did not work out to equal this. The formula says that the k plus first sum should be k squared plus 5k plus 1, but I got k squared plus, and notice it's an 8k instead of a 5k, instead of a plus 1, it's minus 2. So that doesn't equal what the formula says it should equal. And so that means that that is not true for all n contained in the set of integers. So this formula doesn't always work. Maybe it works for a few cases. It does work for the first one, but it's not guaranteed to work for every case. Because the induction step here did not work out to what the formula said it should. So that's what happens when we try to prove something true that's not using the mathematical induction. You can't get that if the kth one works, that the k plus first one always works as well. Okay, because it's actually, in this case, it's not true. That's what happens. And that's the end of the mathematical induction tutorial.